Now we talk about adjoint operator. Adjoint operator plays important role in functional analysis. We start about this. We first talk about definition of adjoint operator. So write this definition now. Let X, Y be inner product spaces. X and Y be inner product spaces. Okay. Inner product spaces. A X to Y be a linear operator. Be a linear operator. Then there exists then a linear operator. Then a linear operator. Then a linear operator. By to X. By to X is said to be an adjoint of A. Is said to be an adjoint of A if Ax y equal to X by here y here X. With respect to y, and this inner product happen. With respect to X, this inner product happen. Then for all X belongs to X and Y belongs to Y. Okay. So this be an adjoint of E. We write in this way. We're now going to further discussion about that uniqueness of this adjoint. Okay. Uniqueness of adjoint. Okay. How we write it? Let X and Y be inner product spaces. Be inner product spaces. And Ax to Y be a linear operator. Be a linear operator. If any adjoint By to X of A exists, if any adjoint Y to X of A exists, then it is unique. Okay. So we'll also prove this. Okay. Now prove here. We write. Suppose that A has adjoint. Suppose that A has adjoint. Let B1, B2 be adjoints of A. Let B1, B2 be adjoints of A. Then what we obtain? Then Axy equal to xb1y. Okay, for all x belongs to x and y belongs to y. Axy equal to b1y, and obviously we add our portion. and axy equal to x b to y for all x belongs to x and y belongs to y. Then we get x b1 y difference b2 y equal to 0. Then this implies that x b1 difference b2 y 0. This implies that b1 y equal to b2 y. Then this implies obviously b1 equal to. So we prove uniqueness of adjoint. Okay. Next we erase this portion and going to further discussion about another thing. Another portion we also discuss about this adjoint. Let Tx to y be a linear operator. Be a linear operator. Then the adjoint of T will be denoted by then the adjoint of T will be denoted by T star. Will be denoted by T star. Thus Txy equal to x T star y for all x belongs to x and y belongs to y. Okay. Then we're going to another theorem. This theorem shows adjoint T exists. That means existence of adjoint T. Okay. This topics will write theorem in way. Let X be a Hilbert space. Let X be a Hilbert space and Y be an inner product space and Y be an inner product space. And T belongs to Bxy. Then there exists adjoint of T for T star exists. Okay. Then we're going to prove of this. Here we write proof. Let y belongs to y and define if y x to k y if y x equal to txy marked as 1. Clearly if y be linear and bounded. With which fy belongs to bx. Okay, then by this representation theorem, then by this representation theorem, there exists unique y belongs to x such that fyx equal to x uy for all x belongs to x. Okay, we marked as 2. Then we erase our portion. Then what we obtain from 1 and 2 we get from 1 and 2 we get txy equal to xuy. Okay, for all x belongs to x. Hence there exists an operator t star. Then there exists an operator t star y to x such that inner product of txy equal to x t star y for all x belongs to x and y belongs to y. Okay, then what we obtain, we now show that t star be linear. We now show that t star be linear. How we show this? We let x belongs to x, y1, y2 belongs to y, and alpha belongs to k. Then x t star y1, y2 equal to tx y1, y2 equal to tx y1 plus txy. Then what happened? This one equal to x t star y1. This one x t star y. Okay. So what we get, t star y1 plus y2 equal to t star y1 plus t star y. Okay. Then we get this one. Next what we see that x t star alpha y1 equal to tx alpha y1 equal to alpha conjugate tx y1 equal to alpha conjugate x t star y1.
Okay.
Then this one equal to x alpha t star y. So what we obtain? We obtain t star alpha y1 equal to alpha t star y.
Okay. Then this implies that
T star be linear. This implies T star be linear. Okay.
now we also
Going to further discussion about something. We erase this portion and going to another theorem of this adjoint operator discussion.
okay.
So we write this statement of this theorem. Let xy be Hilbert spaces. Let x and y be Hilbert spaces. And let t belongs to and let t belongs to bxy. Then t star belongs to dxy with norm t star equal to norm. Now we write proof of this theorem.
Okay. Norm t star equal to norm t.
How we prove it? We write proof first, and then let y belongs to y. Okay. Then t star y square equal to inner product of t star y equal to y of t star y less than equal to t star y inner product of y. This less than equal to norm t star norm y. Sorry, norm t star y here and norm y. Then if y equal to 0, then norm of t star y equal to 0. Then take y not equal to 0. Then norm of t star y less than equal to norm t norm y. Hence t star be bounded. Hence t star be bounded with norm of t star less than equal to norm of marked as 1. Okay. Again, norm of t equal to norm of t star whole star less than equal to norm of t star. Okay, from 1. So this marked as 10. Then by 1 and 2, by 1 and 2, we get norm of t equal to norm of t star. Okay,
So what we obtain?
X, Y be two Hilbert spaces and T belongs to bounded linear operator from X to Y, then T star or adjoint of T exists with adjoint of T norm equal to norm of T. Okay. Then what observation we see here? Observe, we write observation. Okay. Observation, let x equal to y equal to a Hilbert space, and t belongs to bxy. Then what happened? Then norm of t star ty equal to less than equal to norm of t star norm of ty. Okay, less than equal to norm of t star norm of t norm of y. Okay, then we next talk about another properties of adjoint operator. Okay, also erase this portion and also talk about another properties. Now here we write, let x and y be Hilbert spaces, and alpha belongs to k, and t1 t2 and t1 t2 belongs to bxy. Then t1 adjoint and t2 adjoint exist exist so t1 plus t2 adjoint exist, and t1 plus t2 adjoint equal to t1 adjoint plus t2 adjoint, and alpha t adjoint equal to alpha adjoint t. Now we discuss about that. Right here, t1 plus t2 of x, y, this inner product equal to t1 xy, t2 xy equal to x t1 adjoint y, x t2 adjoint y. This equal to x of t1 adjoint plus t2 adjoint. So here we write t1 t2 x y equal to x t1 t2 adjoint of. Then what we write here, this implies x t1 t2 adjoint y equal to x t1 adjoint t2 adjoint. So what we get? We get t1 plus t2 adjoint equal to t1 adjoint plus t2 adjoint. Okay. Now we erase our portion and also going to another part. Okay, so we erase this portion. Next, we write here alpha t1 xy equal to alpha t1 x y equal to alpha t1 x y equal to alpha x t1 adjoint y equal to alpha x, so this alpha in alpha conjugate t1 adjoint y. So what we get alpha t1 xy equal to x alpha conjugate t1 adjoint y. This implies x alpha t1 adjoint y equal to x alpha conjugate t1 adjoint y. So this implies that alpha t1 adjoint equal to alpha conjugate t1. Okay, now we're going to another portion. Also erase this portion and going to another portion now. These properties, let x y z let x y z be Hilbert spaces, be Hilbert spaces, and let x belongs to b x y and t belongs to b y z. Then x adjoint t adjoint and t is adjoint exists. Then ts adjoint equal to s adjoint t adjoint. Now we also write to, or also going to discuss about that. Let x belongs to x and z belongs to z. Then t of s x z equal to t of s x z. This equal to s x t star z. This implies that ts x z equal to sx t star z. This implies x t of s adjoint z equal to the x is adjoint t adjoint z. Then this implies that t is adjoint equal to s adjoint t adjoint. Yeah, z we write. This implies T is adjoint equal to S adjoint T adjoint. Okay,
Then
then here we get some observation right here. If x, y, z are same space, then T is adjoint equal to S adjoint T adjoint. And if put x equal is equal to T, then T square adjoint equal to T adjoints. Okay. In general, obviously, in general, what we done in general, t to the power in adjoint equal to t adjoint for to the power. We're done. Okay. So, so we also discuss adjoint operator. Okay. We also discuss this adjoint operator.
So today we stop here.